All right, so we have this first session on protocols and theory of real-world protocols, I guess. And leading us off with the first talk of the day is Michael Ajej, who's going to be talking about some recent work related to threshold signatures. The work is titled The Best of Both Worlds, Round-Optimized 2PC ECDSA at the cost of only one OLE and applications to embedded cryptocurrency wallets. And I guess you'll have about maybe 22 minutes or so for the talk, and then we'll have some time for questions at the end. Great, thank you. Take it away.
Thanks for the introduction. So I'm Michael Ajej. I'm an applied cryptographer at Fireblocks, and I will present the results of our work with my co-authors Kosti Blor, Geoffroy Couteau, Arik Garlansky, Antoine Joux, and Nikos Makrianis. The full version of this work can be accessed on the ePrint at the link below. So what will guide us through this journey is the following plan. First, I will explain what motivated us to work on this subject. Then I will explain the protocol itself. I will continue by giving new techniques that we use that helped us making our protocol efficient and fast. And I will conclude by listing some of open questions and future works. So let's start by the introduction. You have to know that trillions of dollars were transferred on various blockchains. Most of these transactions are signed using ECDSA, and at Fireblocks alone, we secured around $6 trillion using our current MPC ECDSA solution. So this makes it a target of choice for hackers. And as an example, last February, around $1.5 billion were stolen on Ethereum. In average, blockchains see millions of transactions per day. So these transactions should be highly secure, and we should avoid single point of failure. So it seems that threshold ECDSA is the way to go. What would be the ideal solutions for cryptocurrency wallets? So as always, we want it to be fast. We also want the messages exchanged between parties to be small. And by small, I mean small enough to fit into a QR code to allow offline signing, for example. We also want the number of rounds in the protocol to be minimal, ideally to be optimal, because each round induces latency. And for example, our benchmarks showed that between 2 points located in the same region, for example, in Europe, it could take in average 35 milliseconds, while if the two parties are in different regions, it can go up to 150 milliseconds. And there is one last property that we want for such a scheme, is what we call concurrent security, where parties should be able to sign many transactions in parallel, either using the same key or a different key without compromising on the security. What are the best-in-class solutions for the simplest case of two-party computation for ECDSA? We can see that the first one, Lindell 17, clearly outperforms all the others in terms of computation and communication, but it lacks in terms of number of rounds, and we saw in the previous slide that in this case, it becomes the dominant factor. Moreover, is that it does not offer the concurrent security property that we wanted. And, well, basically all the other solutions, they don't offer all of them at once. And our work stands here. We were able to achieve it in 2 rounds, so which is optimal in this case, for a reasonable amount of time and communication. So I would like to apologize to all of you because of the allotted time for this presentation. I will not go into all the technical and theoretical details of the protocol, but I will focus mainly on the protocol itself, of course, but also on the optimizations that we used to make it efficient and fast. So let's start by explaining now the protocol itself. First, a quick reminder of ECDSA. the key generation, where we sample random scalar and compute the associated point. The signature is done using this formula, and the verification where we simply check that the equality holds. Now, what is a two-party ECDSA? So let's say we have two players, Alice and Bob. They share a key. They only have shares of a secret key, and they want to sign a message M, so they will call the MPC ECDSA functionality, and at the end they will get the signature as if it was signed by the recombined key. In practice, this is implemented using rounds of communication between the two parties until they get the signature. How our protocol works. First, it works best in this setting that is called star-shaped topology, where we have one server serving many clients and signing transactions with each of them, each client sharing a different key with the server, of course. This is the case for cryptocurrency wallet providers. So our protocol, we have two steps. The first one is the key generation, but this protocol is fairly simple and quite common, so I will not go into the details. Just remember that this is an additive split of the key, so at the end the recombined private key is just the sum of the two private shells. The most interesting part is the signature itself. So after the key generation, the server has a private share x2, the client has a private share x1, but also the client knows the public share of the server, uppercase x2. So in this protocol, the server starts first. It samples the random nonce k2, sends the two following points to the client, R2 and Y, Y being basically a proof of knowledge of K2. So once she receives it, the client checks this proof, and if it verifies, samples her private nonce K1 and computes the two associated points R1 and R. She then sends it to the server. R is now the proof of knowledge of K1, so the server can check it, and if it verifies, it extracts the x coordinate of the point R. The client does the same on her side, extract the x coordinate, but also compute the two following values, A and B, as follows. From this point, these two parties will call an OLE functionality, an OLE oracle, that will output the value Y to the server. And from this point, you have to trust me, this becomes a valid signature on the message M as if it was signed by the recombined key x1 plus x2. What is an OLE, or oblivious linear evaluation? So we have two parties, Alice and Bob. Alice has secrets A and B, Bob has a secret X. And the OLE oracle outputs Y such that Y equals A times X plus B. And what we want is that no one learns anything about the secret of the other party. But this is not the OLE I showed you in the previous slide, right? I showed you a modified version of it that takes an additional input, which is a point on the elliptic curve. And this oracle outputs Y if and only if the secret of Bob is a discrete logarithm of the input point. How to instantiate such an OLE? So we have many possibilities. One of them is to use an additively homomorphic encryption scheme, which has the following property, where we can compute an encryption of the sum of two messages M1 and M2 by combining an encryption of M1 with an encryption of M2. From this property, we have another one that is kind of a consequence, where we can compute an encryption of a message times a constant by, again, combining the constant itself with an encryption of the message. And then the instantiation of the OLE is quite straightforward, using the two previous properties and this equality. Now, we have two questions. The first one is, how to concretely implement this scheme, or which scheme should we use to instantiate the OLE. And also, if we look at this simple protocol, we can see that it's secure only in the honest but curious setting. So how do we deal with malicious or dishonest parties? So to answer my first question, we decided to use a PIE encryption scheme, which consists in the three following algorithms. First, the key generation, where we sample by prime n. The encryption is done as follows on the message M, and the decryption uses this formula. But we also make use of some zero-knowledge proofs that we adapted from CGGMP 20. The first one that we call PyMod proves that n is indeed a biprime, but where each prime factor of n is congruent to 3 modulo 4. And the second proof, which we call PyFac, proves that n has no factor larger than the square root of n times a small constant. Notice that I haven't said prime factor here, only factor, but it has an impact on the prime factors themselves, just to be noticed. And more concretely, how do we instantiate such an OLE using PyE? Well, we will use these two amazing properties of PyE encryption. We'll also use the two zero-knowledge proofs that I talked about. And then to instantiate the modified OLE, the one that takes an additional point as input, we will simply make use of an additional proof of knowledge of discrete logarithm, and this is done only during key generation. No need to do it during signature. And now how to deal with dishonest parties. So as I said, we made use of zero-knowledge proofs for the instantiation of the OLE, also during the key generation. But we also need to deal with various algebraic structures. We need with modular integers, we deal with elliptic curves. So the go-to technique in this case is to use integer commitment schemes, and we decided to use the Damgard-Fujisaki one, which is quite simple yet efficient, and that suits perfectly our use case. We used it for both the client and the server, and it works well as follows. It needs first for the setup to generate two strong primes, and it makes use of many exponentiation, either during the setup or so, the commitment, the verification, and the associated zero-knowledge proofs. So the last 2 points are costly operations, right? So we'll see in a minute how we dealt with these pain points. So for that, I would like to introduce additional techniques that we used to make our protocol fast and efficient. And we hope that these techniques will be of great interest for the MPC community and to help making protocol more efficient. So first, I would like to introduce a new class of prime number that we call TAF primes. Before saying what they are, I will just quickly remind what are strong primes. So they are primes that can be written this way, 2 times P0 plus 1, where P0 is also a prime number. And to define TAF primes, we first need a security parameter L, and TAF primes are of this form, 2 times a product of smaller primes PIs plus 1, where each of the PIs are small, or are of size 2 times the security parameter. To the best of our knowledge, this is the first time that this class of prime number is proposed, and we claim that they offer identical security guarantees compared to strong primes in many use cases, at least for all of the ones that we use in our protocol. This is, of course, backed by some argument in the paper, so I invite you to read it. But what is even more interesting about TAF primes is their generation. We used the following algorithm, which is quite simple. First, we sample a pool of small primes PIs, And then we pick a random subset of this pool, multiply them together, multiply it by 2, add 1. And if the result is prime, then we found our candidate. Otherwise, we just reiterate the process. And we got these numbers. And we can see that when we compare the generation time of tough primes versus regular ones for 1.5 kilobits size, we only lose a factor of 1.4. And if we compare it to the generation of strong primes, we have a factor of 50 between the two. And this factor gets better for a bigger size of the generated integer, and it's getting worse between strong and regular primes. So we, of course, applied this generation of tough primes to our protocol. We applied it for the setup of the Damgard-Fujisaki commitment scheme on both the client and the server, and we saw a 15x improvement in our benchmarks. So that was a bit crazy. The second technique I want to talk about is short exponent. So we have first this problem, which is quite well known and well studied, which is called the short exponent discrete logarithm. This is the formal definition, but it means in short that it should be hard for an attacker to solve the discrete logarithm problem when the exponent is short, and by short I mean at least twice the security parameter. And we have another related problem, which is called the short exponent undistinguishability. It says that there is no advantage for an attacker to distinguish between something that has been generated using a short exponent and something that has been generated using a full-size exponent. And these two problems are related. Specifically, the SEI reduces to the SEDL. It has been proven in KK04, but we also proved that the reduction is true in unknown order groups. So we applied this technique at different places. First, we applied it to the PIE encryption in the following way. So first, a small reminder about the formula for the encryption of the message. And this part is the most expensive one, okay? It's an exponentiation. The exponent is n. It's done modulo n square. And we noticed that if we pick rows, so the randomizer, to be already a square modulo n and raised to the power of n modulo n square, it can be pre-computed and be part of the PIE parameters. And of course, it needs to be checked by all the parties that will use this scheme. And the encryptions simply becomes this. We only need to pick a random exponent r of size 2 times the security parameter and compute the following value. This is clearly faster because the computation time of an exponentiation is linear into the bit length of the exponent. Moreover, this is still a valid ciphertext by ciphertext because the right part of the ciphertext still vanishes once raised to the power of phi of n. And we got these numbers when we benchmarked the PIE encryption. So we can see we got up to 15x improvement. Notice that only the PIE encryption can be accelerated this way using the short exponent trick. The decryption still needs a full-size exponentiation. And of course, we used it for the Damgard-Fujisaki one. We also saw a few improvements, but we had to take care of one specific point because some components were used to statistically hide some values, so they couldn't completely benefit from the short exponent trick, yet they were accelerated a bit. So let's jump now to the conclusion. You have to know that this protocol is currently under deployment in real world. It's also being audited, and once the audit reaches the end, it will be released in an open source repository. And then we asked ourselves, can we even further improve the protocol? Can we reduce the computation time? Can we reduce the communication between parties? For example, there was a paper published last year that showed how to combine the PIE encryption with the Damgard-Fujisaki commitment scheme together. So this would definitely reduce the computation and also probably the communication. And last point, we want to dig even further into TAF primes. What would be the implication regarding security if we apply them, if we use them in all the use cases where strong primes are usually used? I guess I'm right on time. And thank you for your attention. This is time for questions.
Thank you. Question? Yeah.
Great presentation. Going off your last point on tough primes, you said you make an argument in the paper about its security. Can that argument be applied to all PIE-based schemes, or is there something specific about your protocol that it applies to?
So the arguments that we explain in our paper, well, basically, we looked at all the state-of-the-art algorithms to solve the factoring problem or to solve discrete logarithm, because they are kind of related. And we saw nowhere that they would give an advantage to an attacker to solve it. So, well, this is only my guess. Some of my co-authors are already working on this. But my guess is that yeah, they are clearly as secure. We'll see. They will hopefully publish a paper soon, so you'll have more details.
Is it possible to instantiate your protocol in, for instance, a CL framework?
In the
CL framework, so using class groups, where you have a subgroup.
Yeah, so that's a great question. So yes, class groups were considered at the very beginning of this work, and we discarded them for two reasons. First, we were not sure that this would be as efficient as using PIE, especially with the short exponent trick. And moreover, this protocol is meant to be deployed, accepted, maybe standardized, or at least some of the techniques. And class groups are not yet adopted by the industry compared to, well, PIE or RSA groups, let's say. So for these two reasons, we decided not to work with class groups. But yeah, this could absolutely work with class groups too.
In a similar vein, did you look at like an LWE-based additive homomorphic encryption scheme to, because that would be PQ and LWE is a bit accepted in the industry.
We looked at the DGHV scheme, FHE scheme, because it would, well, we thought at some point that it would be efficient, but the sizes of the data is very big to be secure, so we discarded this solution. But we didn't look at all the other schemes, but this could be a solution. But again, we want it to be efficient in terms of communication. So, what would be the perfect balance? Something.
PIE is not efficient in communication, is it?
You're right.
I had one quick question about concurrent security. First of all, just a quick question. I mean, you mentioned when you had the table up at the beginning that Lindell 17 is not concurrent secure. Does that mean there's an attack or just no proof of concurrent security?
So in the paper itself, it clearly says that if something goes wrong during the signature, the key should not be used anymore. Otherwise, well, so funds will be blocked in this case, and this is not acceptable. Yeah, wanted to go back to the table, but it's quite far.
That's okay.
So in the case of cryptocurrency wallets, this is definitely not acceptable. So, yeah, this one. It's clearly stated in the paper. And we saw there was a paper published in 2023 at Black Hat, where some cryptocurrency wallet providers implemented Lindell in their solution, but they did not handle well this case of like not using the key anymore if something went wrong.
Yeah.
And they were able to extract the key.
Right, I remember that now. Yeah. So for your work, you said you use zero-knowledge proofs. Do you need proofs of knowledge and extraction, or no?
Yeah, yeah.
So how do
some
you,
of the proofs are
and I assume you make it non-interactive and whatever. So how do you
Exactly.
Do you just assume that Fiat Shamir?
Yeah, we use Fiat Shamir.
Yeah, good. All right, so we're right on time for the next talk. So let's thank the speaker again.
Thank you.